Lots of people are excited by this new utility AI feature brought in state trees for UE 5.5. So today we're going to look at how we can use this utility AI feature to control the state of an NPC. So this character has 4 states. He essentially, 1, either explores the world he's in, 2, if he sees us, he will chase us, 3, if his stamina levels drop, he has to find a well to replenish them, and then at night time he has to go to bed and stay there till dawn and then repeat his lifestyle. The way that utility AI works is that it will calculate a score for each of those 4 states based on our sort of instructions, and then it will choose the state with the highest score and execute it. And then at the end of that execution it will go back and recalculate the scores for each of the available states and thereby choose which state this character will be in. Our setup is simple, so we've got a simple AI character with an AI running a state tree in a world where automatic navigation links have been set up. I've done videos on this, and there is also a day-night cycle that is operating. And the day-night times will control whether he's awake or asleep. And the character has got an AI perception component on it, so it can detect us and choose to chase, and if he can't detect us, to explore. So I've activated both of these state tree plugins and this day sequence plugin. Let's start by creating our first state tree. So if you right click, Artificial Intelligence, State Tree, ours will be a State Tree AI component because we're going to put this on the AI controller. So I'll click that and we'll call that State Tree Utility. And then we can open it. In our asset details, we can maybe set our schemas. So our AI controller, mine is AIC utility. So that's the one I've created. The character is BP utility AI character. So we can set those up as our controller and context actor. And then in our states we can start adding, so we'll add one first state. This will be our utility state action. On this we will then add some child states which you will be able to choose from. So we'll say add child state. Our first one will be explore world. Our next one will be chase player. Then we'll have a sort of go to sleep. And we'll have a 4th state which will be to replenish energy or thirst. So we'll just call that replenish. I think I've just named it as stamina, so I'll say replenish stamina. Now basically the way that utility AI works is if you click on your parent state and you go to the selection behavior, instead of the select in order, there is an option which says try to select children with highest utility, or you can select children weighted by utility. We're going to choose with highest utility. So as it says, it will try to choose the state with the highest utility score. If there is a tie, then it will choose them in order. So we'll set that there. And then what you need to do is when you add tasks to each of these states, you need to add a selection utility in order to calculate a weight. So I've gone ahead and I've created the tasks for each of these states. so that we can focus on how utility AI will actually pick the states to go into. And this is all rather simple. So to explore world, first we find a move to location, and then we move to it. Then we delay, chase player, we find again the location of the player, move to it, go to sleep, we find the actor of a particular class, and then we move to it, and replenish stamina, we look for an actor of a BP well type, move to it, spend some time there replenishing our stamina. And just to help, I've set up also a global task so we can get our day-night sequence from the world, and just one parameter, the bed that we need to go to when we go to sleep. I've shown how you can create tasks like this to get locations and move to them in previous videos, so we won't go into that today. What we are interested in it though is this utility. So how will it select the child with the highest utility? As we said here, there is a selection utility. Now there's two ways that you can do it. One is by using variables that you can access in your state tree, and the other is by creating a consideration, which is a state tree utility consideration. We'll try to do both today, and we'll start off with the sort of accessing the variables via parameters that we've already set. So when it comes to explore world and the chase player tasks, that will be based on whether or not the AI can detect us as a player. So in the AI controller, I've created a AI perception, and when it senses a player, it will set this player sensed variable, and it will send a state tree event using a gameplay tag, which I've set up some gameplay tags for this. So if we go to our explore world first, and under selection utility, click the plus, we've got an option of built-in options of constant, float and enum. We'll choose constant. We'll click that. In the constant, instead of a float, we actually want a bool. So we'll say logic and then we can compare one bool to another. So we want to compare. So the logic here is if the AI controller cannot sense the player, he should explore. So we drop down there, we look for our AI controller reference, and this is the player sense boolean that we just created. And we'll say if that is equal to false, then this will return a score. And the scores are normalized, I think, between 0 and 1. So this would return a score of 1 if the player was not sensed. So if player sensed equals false, this will return a score of 1, and it will enter the explore world tasks. For chase player, we can use exactly the same logic, but we want it to be true. So selection utility, added consideration, we'll use a constant again. We'll say a bool, we want to do the logic, say and, that means one is equal to the other. Now again, we will bind this to our player sensed in our AI controller. And this time we will say if it is true, you return a score of 1. In which case it will enter this state and execute these tasks. So now we've set two selection utility score calculations just based on whether the player is sensed or not. We can test this out, but before we do, I should explain why we've got on the explore world and the chase player events. So if you go to the explore, I've added an on event, and if it receives the event state.chase, I've set up some gameplay tags, chase and explore, replenish and sleep. It will then go back to the utility state to recalculate the score. And the reason is that once it's in a state, it will continue in that state until it gets the finished task. But in our perception, whenever the player is sensed changes, we are just sending a gameplay event, a state tree event, to trigger a change. And that change will force the tree to reevaluate the score. So if it's an explore and it gets the chase gameplay tag event, it will go back, reevaluate the score, and enter chase. If it's in chasing and it loses sight of the player, it will get the explore gameplay event, and it will go back here, reevaluate, and then it will go back into explore. So this should work for these two states. So let's test them out first. Let's play. So he starts off in explore. As he runs, as he sees me, he starts the chasing. He'll come after us. And then he loses sight of us, he goes back to explore. So let's now create a score, utility score for go to sleep and replenish. And we'll be able to explain what this wait means when we do this. So if we go to the go to sleep task, which is just a task where it finds the bed's location and moves to it and stays there for a while before re-evaluating. The way that we do that is we've got our day sequence actor reference, and from there we can get the time. So I've done a video on how you can create a 24-hour day-night sequence. I've called mine BP Sun Moon, and basically it sends out an event when the time is above 8 o'clock to say it's night time, and when the time is between after 4 o'clock in the morning, it says that it's no longer night time. So we can bind to this nighttime boolean in our state tree. So in go to sleep, we can go to our selection utility. Again, we can get another constant here. And we can say, again, put it as a boolean, so a logic and we want to say is the left. So we will get from our global utility, I've got a reference to the day actor sequence, and I can get the is nighttime boolean from there. So is nighttime true? This will return a score of 1. So he should then be going to bed. If I go to replenish, and if we try to do that one now, so selection utility, the way this one works is that the AI character has got an attributes component. The attributes component has got a stamina, and whenever the player is moving, the stamina reduces, and whenever he's in the replenish state, the stamina goes back up to 100. So we can access this stamina from the character. In order to do that, I've sort of created an internal variable and set it to the attributes, because otherwise you cannot gain access to it. So from the replenish, we can get the selection utility, and here we want to get the float value. Now this one is a bit more complicated, because when you go for the float, you get a response curve that you can create, or you can add your own external curve. Then you get an input range which you have to set. And what we want it to do is that when the stamina is less than 40, in other words, when it's between 0 and 40, we want the AI character to go and replenish his stamina or hydration at a well. So under the curve, you can create your own points. So if you press shift and click, and basically the curve goes between 0 and 1. I think it needs to be normalized. So we'll say at 0, if the stamina value is 0, we want the value to be 0. No, we want the value to be 1. We want this to return a score of 1. If I shift and click again, we then want to say if the value is 40, we want to return a value of 1 as well, so between 0 and 40. However, this needs to be normalized, I think, for it to work. So that's where this input range comes in. Our input range for our stamina is between 0 and 100, so we can put that in there. which means that this can be normalized to 0.4. 40 would be 0.4. And at 40 we want to return a score of 1. We then want it to go from there and drop to 0. So shift and click again, and we can basically say if it's from 41 onwards, the value should be 0. So now we get this curve. So from between 0 and 0.4, as in 0 to 40 of stamina, it will give us a score of 1, and then it will drop down to 0 from that point onwards. And we can just make sure that it ends as well, so we can say at 1 it's also 0. So that creates the curve. This is the input range. The float, I think the input range will come in, you can put that as an interval. No, so the input in, so this is where we bind to our stamina variable. So we can go to our actor, and from the attributes there is a stamina value that we can bind to that. Then I think in the input range we need to make that an interval. So that's an interval between 0 and 100. Compile that. So this is using a float value, and if the float value when normalized is between 0 and 40, 0 and 0.4, which is in the range 0 to 100 stamina, in other words when it's less than 40% stamina, this will return a value of 1. Now the problem is obvious straight away, is that they can all potentially return a value of 1, in which case the state tree would just go to the first one that returns the highest value. So this is where the weight comes in. So you can prioritize which one should be more important, have a higher utility based on its weight. So we could say that Explore World has a weight of 1. We want Chase Player to be more important than Explore World, so we give it a weight of 2. So if the scores were the same, it would go to Chase Player. We want Go to Sleep to be more important than these two, so we want that to have a higher weight, because at night we want it to go to sleep, so we give that a weight of 3. And the Replenish Stamina, we might say that whenever its stamina or its hydration or whatever is low, it should always go and replenish regardless of anything, so we give that a weight of 4. And we compile. So if this works correctly, from the root it will come into the utility state action, the parent state. This state has got a selection behavior of select children with the highest utility. On each one of the child states there is a selection utility that we've added, and you can add multiple, so you could have 2 or 3 of these operating together. But ours, for the first 2, it just looks at the AI controller player sensed variable. If it's false, it says yes for Explore World with a weight of 1. For Chase Player, it says if it is sensed is true, it returns 1 but with a weight of 2. In other words, it doubles it. Go to Sleep looks for the time in the day sequence actor, and it says if it is nighttime, then enter Go to Sleep with a weight of 3. So it takes precedence over the previous 2 states. And Replenish, we've looked at this using a float value because we've got a stamina value between 0 to 100, where we've then created this curve, which is a normalized curve between 0 and 1, and added the values. And the value that comes back is the score. We've then bound that to the attributes stamina, told it the interval range is between 0 to 100, and we've given this a weight of 4 because we want it to take precedence over all of the previous states and have the highest utility score if it is valid. So this should work. Now let's go to our main level. I said in our AI controller on the state tree we've added our state tree utility that we're working on. So if we play, so he should then start with exploring. At some point if he sees us, he should start to chase us. He loses sight of us, he goes to explore again. If his stamina drops, so stamina is now dropped, So now he'll go looking for a well. So he goes up to that well up there, and he will now replenish his stamina. So the bar goes up to 100. And now if the time is now past midnight, so now he's got the sleep. So he'll now go searching for his bed. And he will sleep there. And then dawn comes, he sees us again, so he starts chasing. And back to replenish. So our state tree is using the utility score correctly to enter the correct state based on how we've told it to calculate that score. And this score, as I said, can be as complex as you like. So you could have, we've just said like booleans here, but you could also add enums, constants, and have logical and ors to decide which one it enters. A way of calculating a utility score is by using a consideration. So this is a blueprint state tree utility consideration. And this can then be used to calculate a more customizable utility score. And you can create individual considerations for each score calculation, or you can combine them all into one and use some logic to identify the difference. So we just create our first consideration. So state tree consideration blueprint base. And we'll just say this is our state tree consideration utility state. So once you open that, you have the function override. There is a description which you can then allow it to show in, maybe just simply, calculate score. And then there is the main function, which is the get score. So this is the function that will return the score for this utility consideration. And generally, as we said, it's probably best to return a score between 0 and 1, so it's normalized. So for instance, if we wanted to replace this with and calculate it in our consideration, we'd probably need to have access to the AI controller. So we can go here, we can maybe create a variable, AI controller. We can set that as our AIC utility. This will be an input because we want it to be set. Or actually this can be a context, so it's automatically set. And then if we replace this, so if we delete the one that we've just used, and we add our consideration on the explore task, so state tree consideration utility state, our context is set directly. The score will come back here multiplied by the weight. So what we can do is we can get our AI controller, and we could say get player sensed, the variable get player sensed, and then we could return a float based on that. So we could say select, we could say based on that, if the player is sensed, which is true, we want to return 0, and if the player is not sensed, in this case the not sensed for explore, we return 1. We could just put this into a function, so collapse that to a function and say get explore score. We could make that a pure function. Now when you do that, you might get an error. It will say get explore score can modify state, cannot be called on self. So the way that you deal with that is go to the function, click on it and make it a constant, and then that should then work okay. So if it's not sensed, it will return 1. And that will return 1 here. So we can go back there, and this should then work exactly the same. So for some reason there it crashed. So what I've done is I've duplicated the state tree and I've just removed all the old selection utilities we were using. Sometimes you can change them and nothing happens, sometimes it crashes. So we've added our first consideration to calculate a utility score, and this will send back the result of that with a weight of 1. We could create separate considerations to calculate a score for each of these states, or we can find a way of using the same consideration. So we go back to our utility state. What we could do is we could create a state gameplay tag. Of the type gameplay tag. And we could use that to differentiate what score we are looking for. So this could be our, just put that as default, and expose it. We could then on the get score function just take our state gameplay tag, get, do a switch, and then we can add pins to it. So we could add a pin, case 0. We could say this is our explore. So I said I've created gameplay tags state.explore, and that would then use this to return the value. We could add another pin, and this could be state.chase. We've also got replenish and sleep, so I'll go ahead and add those. So I've gone ahead and I've added all the different switch states based on the gameplay tag which we can send in, and then I've created the explore which we saw, the chase score which is exact opposite, and of course making sure that you mark it as constant. Then I've got the sleep score which just needs to know is it night time, and the replenish score which just needs to know whether the stamina is less than 40. And I've exposed those variables that we need here. So all of those will then set a final score value, which is a local variable, and we will send that final score back. So we can then use this one consideration to calculate the different scores for the different states based on gameplay tags. So if we go back to our state tree, in the explore world we just need to make sure we set the tag. So that is state explore. We don't need to set any of these for this particular state. In the chase player, again we can add the same state utility, and we just need to set the tag for chase. Again, it doesn't need those. Go to sleep on the other hand, we add our consideration here. It needs to know the tag, which is state sleep, and it needs to know is it nighttime. So we can get that from our global utility. Our day sequence actor has an is nighttime boolean. And the replenish, we can add the same utility. We can add the state, and it needs to have the stamina. So we can get that from our actor, the attributes, and there's a stamina value. Just like previously, we'll leave the weights. So the explore has a weight of 1, chase has a weight of 2, go to sleep weight of 3, and replenish 4. So that the normalized value coming through will be multiplied by the weight, so that we can prioritize which one takes precedence. I've changed the state tree to the new one that we just created with the considerations, and it should work exactly the same. So he starts to explore. If he sees us, he begins to chase us. Should keep chasing us. And when his energy levels have dropped, he goes to replenish. So he finds himself a well, jumps up there, replenishes his energy. Now the clock says it's midnight, so now he should go and find a bed to sleep in. And he'll stay there till dawn, and then he'll come back and repeat the cycle. So that's how you calculate a utility score using a consideration. And you can either use one consideration like we did to calculate all the scores for the different states, or you could create individual considerations. And again, you could add multiple of these considerations, and the scores would be added up to create a final score. You can mix and match, so you could, as long as it is that replenished stamina, get rid of the consideration and go back to using the one that we did previously. So get a constant, actually get a float, create the response curve, put the input, binding, the range, and you can then mix and match this approach with the considerations. So I've added back the float with its response curve like we did previously on the replenished stamina, and the rest are all using the consideration that we created. Compile that, and again it should work exactly the same. It will explore, chase, and the replenish should work again. So when he runs out of energy, he'll go and replenish and then go to sleep. So that's a quick overview of how you use utility AI in your state trees with this selection behavior, creating your individual states under the parent state for it to consider, and then you can either create considerations like we did here and return a score, or you can use sort of the access to the inbuilt variables and access floats or booleans and all kinds of logic that's available, intervals, maths, logic, and combine them. So the key points to remember are that 1, you need to set the behavior as select children with highest utility. 2, it will then pick the state with the highest score, and you can weight these states so that you can decide which one should take priority if they have the same score. The third thing to remember is that once it enters a state, it doesn't check the score on tick. So it's only when it returns back to here will it check it again. So you can force it to recheck by using state tree events. So it goes back and finds another state. Otherwise, the rest of it's all quite simple. You can sort of combine different ways of calculating the utility, which can be simple or as complex as you like. And overall, this is going to be very useful if you're creating complex behavior, but just want to do so with a simple state tree setup. So I hope that helps explain it.